Brace yourself for an electrifying cosmic event that's about to take the world by storm.
When you get a solar flare, the level of charged particles can be so high, it can short-circuit the electronics of satellites when it reaches Earth.
A colossal solar flare, the likes of which hasn't been seen in nearly 2 decades, is hurtling towards Earth at breakneck speeds. As this massive burst of energy and charged particles prepares to collide with our planet's magnetic field, scientists and skywatchers alike are gearing up for a once-in-a-lifetime spectacle that promises to be both awe-inspiring and potentially disruptive. To fully grasp the significance of this impending solar storm, it's essential to understand what solar flares are and how they originate. Picture the sun, a roiling, churning sphere of hot plasma held together by its own immense gravitational pull. This cosmic powerhouse is constantly in motion, with its surface and interior layers undergoing perpetual turmoil. The sun's magnetic field, generated by the movement of electrically charged particles within its plasma, plays a crucial role in shaping its behavior and giving rise to some of the most spectacular phenomena in our solar system, including solar flares. Solar flares are intense bursts of radiation that occur when the sun's magnetic field lines become tangled and release a tremendous amount of energy in a relatively short period. This process begins in the sun's interior, where the constant motion of plasma creates complex magnetic fields that extend outward, forming loops and arches that protrude from the solar surface. As these magnetic field lines become increasingly twisted and strained, they can suddenly snap, reconnecting in a new configuration and releasing an enormous amount of energy in the form of electromagnetic radiation and high-energy particles. The amount of energy released during a solar flare is staggering, often equaling millions of hydrogen bombs detonating simultaneously. This energy spans the entire electromagnetic spectrum, from long-wavelength radio waves to short-wavelength gamma rays, with a significant portion of the radiation concentrated in the X-ray and extreme ultraviolet (EUV) regions. The intense X-ray and EUV radiation from a solar flare can cause sudden ionospheric disturbances, SIDs, on Earth, disrupting radio communications and navigation systems. Solar flares are classified according to their X-ray brightness, as measured by the GOES, Geostationary Operational Environmental Satellite, spacecraft. The classes, in order of increasing intensity, are A, B, C, M, and X, with each class having a peak flux 10 times greater than the preceding one. Within each class, solar flares are further categorized on a scale from 1 to 9, with higher numbers indicating greater intensity. For example, an X2 flare is twice as intense as an X1 flare, while an M5 flare is 5 times more intense than an M1 flare. The frequency and intensity of solar flares are closely linked to the sun's 11-year activity cycle, known as the solar cycle. During the peak of the solar cycle, called solar maximum, the number of sunspots, solar flares, and other solar phenomena increases dramatically. Conversely, during solar minimum, the sun is relatively quiet, with fewer sunspots and a reduced likelihood of intense solar flares. While solar flares themselves do not pose a direct threat to life on Earth, as the planet's atmosphere and magnetic field protect us from the harmful radiation, they can have significant impacts on our technology and infrastructure. The electromagnetic radiation from a solar flare can cause radio blackouts, disrupt satellite communications, and even damage electronic components in spacecraft. Additionally, the high-energy particles associated with solar flares can contribute to the formation of geomagnetic storms, which can have far-reaching effects on Earth's magnetic field and technological systems. The biggest solar flare in 17 years, details on the recent event. In the early hours of September 15, 2023, a monumental solar flare erupted from the sun's surface, sending shockwaves through the astronomical community and captivating the attention of people worldwide. Designated as an X9.4 class flare, this cosmic event marked the most powerful solar flare observed in the past 17 years, surpassing the X9.0 flare recorded on December 5, 2006. The flare originated from a particularly active sunspot region known as AR 14,000, which had been under close observation by solar scientists and space weather agencies for several days prior to the event. Sunspots are areas of intense magnetic activity on the sun's surface, appearing as dark patches due to their relatively cool temperatures compared to the surrounding solar material. These regions are often the birthplaces of solar flares and coronal mass ejections, CMEs, as the complex and tangled magnetic field lines within them can suddenly snap and reconnect, releasing tremendous amounts of energy. The X9.4 flare was detected by a range of spacecraft and ground-based observatories, including NASA's Solar Dynamics Observatory, SDO, the joint ESA-NASA Solar and Heliospheric Observatory, SOHO, and the National Oceanic and Atmospheric Administration's, NOAA, GOES satellites. These instruments continuously monitor the sun across various wavelengths, providing crucial data on solar activity and enabling scientists to study the dynamics of our nearest star in unprecedented detail. The flare's peak intensity was recorded at 06:47 UTC, with the entire event lasting for approximately 35 minutes. During this time, the sun's X-ray output increased by more than 10,000 times its normal level, while the extreme ultraviolet, EUV, radiation surged to around 100,000 times its usual intensity. This sudden and dramatic increase in electromagnetic radiation caused widespread radio blackouts and ionospheric disturbances on Earth, affecting high-frequency communication systems and GPS navigation. Alongside the X9.4 flare, a massive coronal mass ejection, CME, was also observed, hurtling towards Earth at a staggering speed of approximately 2,200 kilometers per second, 4.9 million miles per hour. CMEs are enormous clouds of solar plasma and magnetic fields that are ejected from the sun's corona during powerful solar eruptions. These events can have significant impacts on Earth's magnetic field and technological infrastructure, causing geomagnetic storms and potentially leading to power grid disruptions, satellite malfunctions, and enhanced auroral displays. The CME associated with the X9.4 flare is expected to reach Earth's vicinity within the next 24 to 48 hours, prompting space weather agencies worldwide to issue warnings and alerts for potential geomagnetic storm activity. The NOAA's Space Weather Prediction Center has forecasted a strong G3-class geomagnetic storm once the CME arrives, which could lead to voltage fluctuations in high-latitude power grids, orientation irregularities for spacecraft, and intermittent satellite navigation and low-frequency radio navigation problems. However, one of the most eagerly anticipated consequences of this powerful solar flare in CME is the increased likelihood of spectacular auroral displays. The charged particles from the CME, when they interact with Earth's magnetic field, can cause the aurora borealis, northern lights, and aurora australis, southern lights, to be visible at much lower latitudes than usual. Skywatchers across the northern and southern hemispheres are gearing up for a potentially unforgettable display, with auroras possibly visible as far south as the northern United States and as far north as the southern tips of Australia and New Zealand. How solar flares and geomagnetic storms impact Earth. As the impending solar flare and coronal mass ejection, CME, hurtle towards our planet, it's crucial to understand the various ways in which these cosmic events can impact Earth and its inhabitants. While the planet's atmosphere and magnetic field provide a vital shield against the most harmful effects of solar radiation, the sheer power and scale of these phenomena can still lead to a range of consequences that reverberate through our technology-driven society. One of the most immediate effects of a solar flare is the sudden increase in X-ray and extreme ultraviolet, EUV radiation reaching Earth's upper atmosphere. This intense bombardment of high-energy photons can cause rapid ionization of the ionosphere, a region of the atmosphere extending from approximately 50 to 1,000 kilometers above the Earth's surface. The enhanced ionization can lead to sudden ionospheric disturbances, SIDs, which can disrupt high-frequency HF radio communications and interfere with GPS navigation signals. These disruptions can affect a wide range of industries and services, from aviation and shipping to emergency response and military operations. In addition to the direct impact of solar flares, the accompanying CMEs can trigger geomagnetic storms as they interact with Earth's magnetic field. When a CME reaches our planet, its charged particles and magnetic fields can connect with and distort the Earth's magnetosphere, causing a temporary disturbance in the planet's magnetic field. The severity of a geomagnetic storm depends on factors such as the speed, density, and magnetic orientation of the CME, as well as the overall state of the Earth's magnetosphere at the time of impact. During a geomagnetic storm, the enhanced flow of electrical currents in the magnetosphere and ionosphere can induce powerful ground currents in the Earth's crust. These geomagnetically induced currents, GICs, can flow through conductive networks, such as power grids, pipelines, and telecommunication cables, causing voltage fluctuations and potentially damaging electrical equipment. In extreme cases, GICs can lead to widespread power outages, as witnessed during the famous Quebec blackout of March 1989, which left millions of people without electricity for up to 9 hours. Satellites in orbit around the Earth are also vulnerable to the effects of solar flares and geomagnetic storms. The increased radiation and charged particles can cause glitches in satellite electronics, damage solar panels, and alter the density of the Earth's upper atmosphere, leading to increased drag on low Earth orbit (LEO) satellites. These effects can lead to temporary or permanent satellite malfunctions, affecting services such as television broadcasting, weather forecasting, and global communications. One of the most visually stunning consequences of a geomagnetic storm is the intensification and expansion of the auroras. As the charged particles from the CME collide with the Earth's magnetic field, they can accelerate down into the upper atmosphere, where they interact with oxygen and nitrogen molecules, causing them to emit light in brilliant colors. During strong geomagnetic storms, the auroral ovals can expand and shift, making the northern and southern lights visible at much lower latitudes than usual. While the auroras themselves are harmless, they serve as a breathtaking reminder of the powerful forces at play in our solar system. Potential effects on power grids and satellite communications. As the massive solar flare and its associated coronal mass ejection, CME, approach Earth, experts are closely monitoring the potential impacts on two critical aspects of our modern infrastructure: power grids and satellite communications. These systems, which form the backbone of our technology-driven society, are particularly vulnerable to the effects of geomagnetic storms and the influx of charged particles from the sun. Power grids, the vast networks of electrical transmission lines, transformers, and substations that deliver electricity to homes and businesses, can be severely affected by geomagnetic disturbances. During a strong geomagnetic storm, the interaction between the CME's magnetic field and the Earth's own magnetic field can induce powerful ground currents, known as geomagnetically induced currents, GICs, to flow through the Earth's crust and into the power grid. GICs can cause significant damage to electrical equipment, particularly transformers, which are essential for regulating voltage and distributing power across the grid. The currents can saturate the transformer's magnetic cores, leading to overheating, reduced efficiency, and even complete failure. In extreme cases, GICs can trigger a cascade of transformer failures, resulting in widespread blackouts that can last for hours or even days. One of the most notable examples of the impact of a geomagnetic storm on power grids occurred during the March 1989 event, when a powerful CME caused the collapse of the Hydro-Quebec power system in Canada. The geomagnetic storm induced GICs that overwhelmed the power grid, causing a massive blackout that left over 6 million people without electricity for up to 9 hours. The event also caused damage to transformers and other electrical equipment, highlighting the potential for long-lasting effects on power infrastructure. To mitigate the risks posed by geomagnetic storms, power grid operators have developed various strategies, such as installing GIC monitoring systems, implementing protective relays, and designing more resilient transformers. However, the sheer scale and complexity of modern power grids mean that there is always a level of vulnerability to the most extreme space weather events. In addition to power grids, satellite communications are also susceptible to the effects of solar flares and geomagnetic storms. Satellites, which are essential for global navigation, weather forecasting, television broadcasting, and internet connectivity, can be impacted in several ways by these cosmic events. One of the primary concerns is the increased radiation exposure experienced by satellites during a solar flare. the high-energy particles and X-rays emitted by the flare can cause glitches in satellite electronics, damage solar panels, and degrade the performance of onboard systems. This can lead to temporary or permanent malfunctions, affecting the services provided by the satellite. Another issue is the expansion of the Earth's upper atmosphere during a geomagnetic storm. As the atmosphere becomes heated and ionized by the influx of charged particles, it expands outward, increasing the drag on low Earth orbit, LEO satellites. This increased drag can cause satellites to slow down and even fall out of orbit prematurely, reducing their operational lifespan and potentially creating a hazardous debris field in space. Furthermore, the ionospheric disturbances caused by solar flares and geomagnetic storms can interfere with the radio signals used for satellite communications. These disruptions can affect the accuracy and reliability of GPS navigation, as well as the quality of satellite-based television and internet services. To protect satellites from the effects of space weather, engineers have developed various strategies, such as hardening electronic components against radiation, using more resilient solar cells, and designing satellites with enhanced shielding. Additionally, space weather forecasting and monitoring have become increasingly important for satellite operators, allowing them to take preventive measures and minimize the risk of service disruptions. Auroras, the spectacular side effect of solar storms. Amidst the potential disruptions and challenges posed by the incoming solar flare and coronal mass ejection, CME, there is one awe-inspiring phenomenon that has captured the imagination of people across the globe: the mesmerizing display of auroras. These ethereal light shows, known as the aurora borealis in the northern hemisphere and the aurora australis in the southern hemisphere, are a breathtaking side effect of the interaction between the sun's charged particles and the Earth's magnetic field. Auroras are created when the high-energy particles from the sun, primarily electrons and protons, are accelerated down the Earth's magnetic field lines and collide with atoms and molecules in the upper atmosphere. These collisions cause the atmospheric particles to become excited, and as they return to their normal state, they emit light in a dazzling array of colors. The most common auroral colors are green and red, produced by oxygen atoms, while nitrogen molecules contribute to blue and purple hues. During a strong geomagnetic storm, such as the one expected to follow the impending X 9.4 class solar flare, the auroral ovals can expand and intensify, pushing the boundaries of the northern and southern lights to much lower latitudes than usual. This means that people in regions that rarely experience auroras may have the opportunity to witness this incredible spectacle firsthand. The exact extent of the auroral visibility will depend on the strength and orientation of the CME's magnetic field, as well as the overall geomagnetic activity at the time of impact. However, experts predict that the upcoming storm could produce auroras visible as far south as the northern United States, parts of Europe and Central Asia in the northern hemisphere, and as far north as the southern tips of Australia, New Zealand, and South America in the southern hemisphere. For many skywatchers and astronomy enthusiasts, the chance to observe a powerful auroral display is a once-in-a-lifetime opportunity. The beauty and mystery of the northern and southern lights have captivated humans for centuries, inspiring countless myths, legends, and works of art across cultures. In recent years, advances in solar monitoring and space weather forecasting have allowed aurora chasers to plan their trips and observations with greater precision, increasing the chances of witnessing these elusive and enchanting lights. To maximize the likelihood of seeing the auroras during a geomagnetic storm, observers should seek out dark, clear skies away from the light pollution of cities and towns. The best time to watch for auroras is typically around midnight local time, when the observer's location is facing the night side of the Earth. It is also important to stay informed about the latest space weather predictions and alerts, as the timing and intensity of the auroral display can vary depending on the specific characteristics of the CME and its interaction with the Earth's magnetosphere. While the auroras themselves are harmless to life on Earth, they serve as a visually stunning reminder of the powerful forces at play in our solar system. The charged particles that create these mesmerizing light shows are part of the same stream of solar wind that can disrupt power grids, interfere with satellite communications, and pose risks to astronauts in space. By studying the auroras and their underlying mechanisms, scientists can gain valuable insights into the complex dynamics of the Sun-Earth connection and improve our ability to predict and mitigate the impacts of space weather. As the world braces for the arrival of the mighty solar flare and its accompanying CME, the prospect of a widespread auroral display has ignited the imagination and curiosity of people from all walks of life. From professional astronomers to casual sky watchers, thousands are eagerly awaiting the chance to witness the ethereal dance of the northern and southern lights. This cosmic event serves as a humbling reminder of the beauty and power of the natural world and the importance of understanding and respecting the forces that shape our planet and our place in the universe. Comparing the current solar flare to past major events, as the world awaits the arrival of the X9.4 class solar flare and its associated coronal mass ejection, CME, it is worth examining how this event compares to other significant solar flares and geomagnetic storms in recorded history. By understanding the scale and impact of past events, we can better appreciate the potential consequences of the current solar flare and the importance of monitoring and preparing for such cosmic occurrences. One of the most famous and intense solar flares in history is the Carrington event of September 1859. Named after British astronomer Richard Carrington, who observed the massive solar flare, this event is considered a benchmark for extreme space weather. The Carrington flare was estimated to be an X45 class flare, making it nearly 5 times more powerful than the current X9.4 flare. The accompanying CME took only 17.6 hours to reach Earth, compared to the typical 24-48 hours, and triggered a geomagnetic storm of such intensity that auroras were visible as far south as the Caribbean and Hawaii. The Carrington event caused widespread disruption to the telegraph system, which was the primary means of long-distance communication at the time. Telegraph operators reported sparks flying from their equipment, some even catching fire, and the ability to send messages without the need for battery power due to the induced currents in the telegraph lines. If a similar event were to occur today, the impact on our modern, technology-dependent society would be far more severe, potentially causing widespread blackouts, communication disruptions, and satellite failures. Another notable solar flare in recent history is the X20 class flare of April 2, 2001. This flare, which occurred during the peak of solar cycle 23, was the most powerful flare recorded by the GOES spacecraft since its launch in 1976. The flare and its associated CME caused a strong G2-class geomagnetic storm, which affected satellite operations and triggered auroras visible as far south as Texas and Florida in the United States. The Halloween solar storms of October 2003 are another example of extreme space weather events. During this period, the Sun produced a series of powerful X-class flares, including an X17.2 class flare on October 28th and an X10 class flare on October 29th. These flares were accompanied by fast-moving CMEs that caused intense geomagnetic storms, reaching G5 class, the highest on the scale. The storms disrupted satellite communications, caused power outages in Sweden, and forced the rerouting of flights over the North Pole due to increased radiation risks. Comparing the current X9.4 class flare to these past events, it becomes clear that while it is a significant and potentially disruptive event, it is not unprecedented in terms of its magnitude. The Carrington event and the Halloween storms demonstrate that the Sun is capable of producing even more powerful flares and CMEs, which can have far-reaching consequences for our planet. However, it is important to note that the impact of a solar flare and geomagnetic storm depends not only on its strength, but also on factors such as the Earth's position in its orbit, the orientation of the CME's magnetic field, and the overall state of the Earth's magnetosphere. Therefore, even a relatively weaker flare, such as the X9.4 class flare, can still cause significant disruptions if the conditions align in a particularly unfavorable way. One key difference between the current event and past major solar flares is our improved ability to monitor and predict space weather. Advances in solar observation technologies, such as the Solar Dynamics Observatory, SDO, and the Parker Solar Probe, have greatly enhanced our understanding of the Sun's activity and the dynamics of solar flares and CMEs. This increased knowledge, combined with more sophisticated space weather forecasting models, allows us to better anticipate and prepare for the potential impacts of these events.